Welcome to my channel Cherish Physics. Subscribe my channel and keep watching. Today we are going to see the topic viscosity. In common, the term viscous is said to be stickiness of the liquid. In physics, we analyzed the term viscosity in terms of density, velocity and flow of the liquid. See the first picture. Consider one is water and another one is diesel or honey. If we pour it to a beaker, the flow of water is faster than the flow of honey. This is due to the frictional force or tangential force between the adjacent layers of the liquid, which resist the relative motion of the liquid. This property is said to be viscosity, and the frictional force or tangential force is called viscous force. See the second diagram. Water is flowing through a pipe. Consider there are several horizontal layers. At the center of the pipe, the velocity of water is high and it is low near the wall of the pipe. If we draw a velocity profile, its shape is parabolic. The velocity gets increases from the pipe wall to the center. The frictional force, that is the viscous force, between the adjacent layers mainly depends upon the density of the liquid. Both liquid and gases exhibits viscosity. Liquids are much more viscous than gases. Viscosity of liquid due to molecular attraction between the molecules of neighboring layers. For example, if water flows in a pipe means it is between adjacent layers. But the viscosity of gas is not due to the intermolecular attraction as the molecules are far apart. It is due to the sharing of momentum of molecules between neighboring layers. In one word to describe viscosity means it is similar to friction. Next, let us see the coefficient of friction. It is implied by the Greek letter eta. Frictional force is an opposing force. So, Newton's third law here comes into play. By Newton's law, the viscous force depends upon the area of cross-section of the tube and the velocity gradient. In the diagram, I have considered two layers of thickness dx and one is of velocity v and another one is of velocity v plus dv. Mainly, the frictional force is the opposing force, so it has negative sign. F is proportional to a into dv by dx. If we include the proportionality constant eta, then F is equal to minus eta into a into dv by dx. Eta is the coefficient of viscosity and eta equal to F divided by a into dv by dx. Its unit is Newton second per meter squared and its dimensional formula is m L to the power minus 1 T to the power minus 1. And in my channel I have derived the dimensional formula for various physical quantities. If you want to know how the dimensional formula comes means watch my videos. Next let us see the flow of liquids. It is of two types, streamline flow and turbulent flow. First one is streamline flow. It is also called as laminar flow. See the first diagram. Its flow looks uniform. In the second diagram I have considered 3 points A, B, C in the path of the liquid and at each point the velocity is not same, so I have taken it as v1, v2 and v3. Though it is a streamline flow, the velocity of every particle crossing a particular point A, B, C is the same as the preceding particle and it also follows the same path. In streamline flow, the velocity of the fluid does not exceed the critical velocity. If suppose it exceeds the critical velocity, it loses its steadiness. That disorderliness flow of liquid is said to be turbulent flow. This zigzag motion results eddy currents, which is nothing but small loops, which leads to the loss of energy. We can find whether the flow is streamline or turbulent with the help of Reynolds number. If the value of Reynolds number is less than 2000, then the flow is said to be streamline flow. If suppose it is greater than 4000, then it is said to be turbulent flow. Between the range, the flow is said to be transitional. But most of our reference books, the value differs. These value ranges are given in our reference books. Okay, let us see what is Reynolds number. It is a pure or dimensionless number. It determines the type of flow of liquid through a pipe. Note down that it only determines the type of flow through a pipe. It is the ratio of inertial force to viscous force and it obeys the law of similarity. If you want to know what is the law of similarity means, text it in the comment box, I will explain. The formula of Reynolds number is Re equal to Vc into rho into d divided by eta, where Vc is the critical velocity and rho is the density of the liquid, d is the diameter of the pipe, and eta is the coefficient of viscosity of the liquid. Next topic, Stokes' law. Stokes' law experiment is mainly to find the terminal velocity. When a small metallic sphere drops through a highly viscous liquid, it experiences a viscous force. Stokes performed many experiments on the motion of small spherical bodies in different fluids and concluded the viscous force acting on the spherical body depends on the coefficient of viscosity of the liquid, radius of the sphere, and the velocity of the spherical body. F equal to k into eta AV. Experimentally, Stokes found that k is equal to 6 pi. Hence, F equal to 6 pi eta AV, and this is Stokes' law. Next is the experimental determination of terminal velocity. The terminal velocity is the constant velocity acquired by the body while falling through a viscous liquid. When it attains a constant velocity means if there is no net force acting on the spherical body, the weight of the sphere acting downwards, and the viscous force, and Fb is the buoyant force, it also acting upward, which is the upward thrust. At one stage, the weight of the sphere balances the upward forces. Hence, W equal to Fv plus Fb, that is viscous force plus buoyant force. Weight of the sphere W equal to mg, which is equal to 4 by 3 pi a cube rho g, where 4 by 3 pi a cube is the volume and rho is the density of the sphere, a is the radius of the sphere, g is the acceleration due to gravity, and according to Stokes' law, the viscous force Fv equal to 6 pi eta Av, the buoyant force Fb equal to mg, which is equal to 4 by 3 pi a cube sigma g, where sigma is the density of the liquid. On substituting and simplifying, finally we get the terminal velocity equation V equal to 2 divided by 9 into a squared into rho minus sigma into g divided by eta. In the tall jar, we have marked 2 points B and C of distance x, which is well below the free surface of the liquid. Between B and C, the sphere attains the terminal velocity, that is constant velocity. The liquid filled in the tall jar should be a highly viscous liquid like castor oil. By performing the experiment with various spherical balls of same size, we can find the coefficient of viscosity of the castor oil. In this experiment, we have noted the time taken to cross. In this experiment, we have noted down the time taken between the points B and C. We know velocity equal to distance by time, that is V equal to x divided by t. On substituting, finally we get the coefficient of viscosity eta equal to 2 divided by 9 into a squared into rho minus sigma into g into t divided by x. The terminal velocity is proportional to the square of the radius of the metallic sphere, that is, V is directly proportional to a squared. The points I have given here explains the terminal velocity. If sigma is greater than rho, then rho minus sigma becomes negative, which results negative terminal velocity. Hence, it moves in the upward direction. For example, air bubbles rise up through water or any fluid, or bubbles rise up in the soda water. Another example is the clouds in the sky to move in the upward direction. Next, let us see some practical application of Stokes' law. The larger raindrops hurt us more than the smaller ones, and a man coming down with a parachute acquires constant terminal velocity. Next is the Poiseuille's flow method. It is also used to determine the coefficient of viscosity of the liquid. In this experiment, Poiseuille analyzed the steady flow of liquid through a capillary tube. He made several conditions. First one, the flow should be a streamline flow, and the capillary tube kept horizontal so that gravity does not influence the flow of the liquid, and the pressure at the end of the tube is uniform over the cross section of the tube. The diagram represents the capillary tube of radius r and length L. The volume of the liquid flowing per second in the capillary tube depends on the coefficient of viscosity, the radius of the capillary tube, and the pressure gradient. The letter V implies the volume of the liquid flowing per second. V equal to pi r to the power 4 P divided by 8 eta L. And this is Poiseuille's equation. In this experiment, Poiseuille made several assumptions. The first one is the flow of the liquid should be streamlined and parallel to the axis of the tube. Second one, there should be no radial flow of liquid. Third one, pressure over any area of cross section at right angle to the axis of the tube is constant. Fourth point, the velocity of the liquid layer in contact with the wall of the tube is 0. Let us see its limitations. The critical velocity, which determines the flow of the liquid, and its formula is Vc equal to K into eta divided by rho into R, where K is the Reynolds number, eta is the coefficient of viscosity, and rho is the density of the liquid, and R is the radius of the capillary tube. In that equation, K, eta, rho are constants, R is the only variable, and Vc is inversely proportional to R. As R increases, Vc decreases. That is, if the velocity of the liquid exceeds Vc, the critical velocity, the flow becomes turbulent. So, Poiseuille's formula does not hold good for tubes with wider bore. Next is the determination of coefficient of viscosity by Poiseuille's flow method. The term V implies the volume of the liquid flowing per second. Instead of V, we can write it as V by T. This V implies the volume of the liquid. And pressure P is equal to H rho G. By substituting and simplifying, we get eta equal to pi H rho G R to the power 4 into T divided by 8L into V. Next topic, applications of viscosity. By knowing the value of the coefficient of viscosity, we can choose a suitable lubricant for specific machines, because as temperature increases, the velocity of the liquid decreases. It is also used to determine the molecular weight of organic liquids. Third point, blood circulation through arteries and veins depends upon the viscosity of the fluids. Fourth point, highly viscous liquid is used to damp the motion of some instruments as a brake oil in hydraulic brakes. Thank you.